seen in a while, so let's jump right on in here. Now, y'all, I'm labeling a point right here. The coordinates of this point, and it's easy to verify, is 6, 14 thirds. Okay. I mean, this is really cool. Not this part, but just what follows from it. So that's 6, 14 over 3. All right, and again, that can be easily verified by just putting 6 in right here. If you put 6 in right here, you get 2 times 7 over 3, which is 14 over 3, okay? Now notice that's believable because this is the point 5, okay? Now, y'all, all of these points on the inside of here, I've tried to get them labeled. I think I missed right here. These are called lattice points, and they're just integer coordinates. Like, for example, right here, this would be 3, 5. That's an integer coordinate. 1, 5 integer coordinate, and they're all on the interior of this green box determined by this line. Notice this is the point right here, 9, 7, which clearly satisfies this. So you see this line kind of bisects this box, I guess you would say. All right. Now another thing I want to point out also is this notion of the floor function. The floor of 14 over 3, floor of 14 over 3, y'all, this is sometimes called the greatest integer function. It's the greatest integer that's less than, let me get this written here, 14 over 3 floor. This is actually equal to 4. Okay, and it's not hard to calculate that really. 12 over 3 is 4, right? 15 over 3 is 5. Okay, so the floor of this number is 4. Okay, but notice, and this is where it gets really cool. There's exactly 4 lattice points directly underneath this line. Look, 1, 2, 3, 4 on the interior, right? You don't count this one. These are the 4, 1, 2, 3, 4 of them, right? And that's the floor of 14 thirds, which is a point on this line that determines everything. So you got an above and below thing happening here, okay? And the same kind of thing happens all the way across. Notice over here at 1, you don't have anything underneath on the interior, right? So now let's go down and we'll make this even clearer here. This is just so cool. All right, and you can see, folks, you can count all these up yourself. The one we just did, the example we just did, is right here. Okay, and that's just one example. That's all I'm going to do. I think that's all you want to see or need to see. All right, but notice we just went all the way across and we get this result here. 1 plus 2 plus 3 plus all the way across. And y'all, this turns out to be equal to 24, I believe. Let me get some more space here. This irritating screen, I wish I could figure this out so much. But I think that does add up to 24. God, it makes me so mad. I just can't figure out this screen sometimes. Okay, now y'all, let's count them together here, okay? Look, we got 1, 2, 3, 4 right here. 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 14, 15, 16, 17, 18, 19. That was close right there. 19, 20, 21, 22, 23, 24. Okay, again, if you count up all of those, you should get 24. You may want to try it going from left to right, like this, like go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay? So again, we do get 24 right there. And that actually is the sum of all this stuff. Now, what's really neat about this, what's really cool about this that I like a lot is that you can do a general pattern right here. You can do a general pattern that relates back to the box. In other words, you could think of this as, we'll call it, I guess we can use the letters B and A. Those are kind of common. So if you think of this as B over A, this, okay, floor, all right, and then this would be plus 2B over A. It's 2B over A, and let me just do the dots here so I won't have to keep writing. Plus, all the way over here, this would be the same as plus B minus 1 over A. Let me erase that. Okay, so this would be plus B minus 1 over A. Okay, but now here comes the really fun part that actually establishes the identity. This whole thing would be B minus 1 and you can see it just by looking at the square. B minus 1 times A minus 1 all over 2. So you see, this is the general identity, and you can tell why it's true. Like in this case right here, for the 24, what did we have? We had 9 and 7. So notice that. Let me get this together here. We had 9 and 7, so this would be the very same thing. Let me just write it down directly above it if I can fit it in here. 9 minus 1 which is 8, of course, just to see the pattern. Okay, 9 minus 1 times 8 minus 1, or 7 minus 1, excuse me. All over 2. Now the fun part's coming, and you've probably already seen it. I'm just irritated that the screen moves every now and then. I'm not sure why. Okay, over 2. Okay, so 8 times 6 is 48, divided by 2 is the 24 that you see right there. Okay, now, but it's the very simple interpretation. There's just as many lattice points above this line as there are below this line, right? Just as many lattice points exist above this line, interior lattice points, as exists below the line. So that's it, man. And to me, that's just neat. I never thought you could do, I just thought floor functions were kind of dead, but there's a lot of geometrical interpretation going on right here. And this is the general truth. Now, something I didn't prove is that I think for this identity to hold right here, the floor of B over A plus the floor of 2B over A plus dot dot all the way out to the floor of B minus 1 over A, I think A and B probably have to be relatively prime. I'm not sure. I believe that's true. So A and B, and we write it like this: A comma B relatively prime. A and B share no common factors other than 1. Okay, So they have to be relatively prime, or co-prime, I think, is the terminology that's a little more prevalent these days. But anyway, y'all, I hope you enjoyed that. Sorry about the screen problems. I'm trying to fix them.